Okay, so can you all see this? See my screen?
Yes, sir.
Okay, good. So in the first part of the course, as I told you earlier as well, in the first part of the course, you will be looking at the instructions of a computer. Now, you might be wondering, some of you might be wondering, what are these instructions and what do they do and all that. So instructions basically is the language of the computer. So now in your previous course CO222 programming methodology, you looked at how you can write programs using a high level language like C. Now, when you write a program in C, you cannot execute that program directly on a computer because the computer cannot understand the C code. So if you want to execute a program written in a language like C, you first need to convert that program into something that the computer can understand. So what computer can understand is the instructions or the assembly. So we call the instructions as the language of the computer because of this reason. And in this course, you will be looking at this language of the computer. So now when you are going to look at the language of the computer, the first term you come across is the instruction set. Now you know, I think you already have got a basic idea of what an instruction set is in the introduction to this course session. And anyway, the instruction set is the set of commands that the computer can understand. So it is a collection of instructions that the computer can understand. A computer meaning a processor basically. So when you consider different computers, they have different instruction sets. That is because they can understand different sets of commands. So basically the processors or computers you have worked with so far might be the Intel processors. So the language an Intel processor can understand is or could be different from a language some other processor can understand. So there are processors other than Intel, if you don't know. So there are processors such as ARM, MIPS, and there are so many other processors available, and they all have different sets of instructions. But if you look at the core components or core concepts in all those instruction sets, they are very similar. So there are many aspects that are common to all of these instruction sets. So studying about one instruction set will be most probably enough to work with some other instruction set as well. So if you consider early computers, they had very simple instruction sets. In fact, like if you consider instructions, they most probably are going to be basic operations that you can perform with the processor. So basic operations a processor can perform are things like addition, subtraction, multiplication, and things like that. So an instruction set is consisted, or an instruction set consists of these commands that the hardware processor can understand or execute. So if you consider an early processor, they had a very simple instruction set, and the implementation of these processors are also simple. And So with that in mind, if you consider modern computers, you might think that they are very complex. So in a way, they are complex, but if you consider the instruction set or the basic operation supported by a processor, they are also going to be simple. So when you study about the instructions and instruction sets, you will understand the basic operations supported by a processor are going to be simple. So complex programs, you can convert them into simple operations and then execute on a processor. So that is the basic idea. And now I told you that there are many processors available in the market. So the most common example would be the Intel processor, because most of your PCs might be equipped with the Intel processors, Intel x86, for example. Now, but something that you might not know is that there's a very popular processor, and it's actually the processor that is used by most of the devices that are available today, and that processor is called ARM. And in this course, you will be studying about the instruction set of the ARM processor, or the basic operations that are supported by ARM processor. And when you learn the instructions of ARM processor, it will not be that hard to move to something like Intel as well. So uh, so the example we will be using in chapters 2 and 3 would be the ARM processor. And so this is the most popular 32-bit instruction set in the world. And you can learn more about ARM processor and its instruction set by going into this link available on the slide. And if you look at the numbers, you can see that in 2008, there were 4 billion ARM processors shipped. So that itself means that how popular this ARM processor is. And so if you look at the embedded market, embedded core market, or embedded devices, meaning things that are not general purpose computers. So embedded devices, an embedded device refers to something that is not a general purpose computer. So more about embedded systems, embedded devices, you will learn in upcoming courses as well. Anyway, embedded devices are devices that are not like your PC or laptop or things like that. So examples for embedded devices are mobile phones, consumer electronics, and network storage equipment. So the controller you see in your automatic washing machine. So those things are embedded devices, and most of these embedded devices are equipped with this ARM processor. So the best example is your Android phone. So most of the Android phones are equipped with ARM processors. So these instructions we will be learning, or the assembly programming we will be learning in this course, you can use it to directly program the processor available in your Android phone. And this is like the typical of many modern RISC ISAs. I hope you got some idea, or you got an introduction to what RISC and CISC architectures are. So seems like Dr. Isuru is here. Now, so this is an example for a RISC architecture, reduced instruction set computer. And the difference between RISC and CISC architectures, you might learn in the course as well. So if you want to look at the ARM assembler instructions, or the instructions available in the ARM architecture, you can refer to these appendixes measured, and they are available in the reference book. So that's a basic introduction to the ARM processor and the popularity and the popularity of the ARM processor. And so it's going to be like learning ARM assembly will be very useful. In one thing is that you can directly apply this ARM assembly to program a processor that is available in something like your Android phone, and also these concepts that you learn will be helpful in learning another assembly language as well, something like Intel x86 assembly. So they are going to share a lot of things. And first we can look at the arithmetic operations supported by the ARM processor. So a typical high-level program you write in C contain a lot of arithmetic operations. Now you already know, I think you already have experience about this because you do a lot of addition, subtraction operations in the high level in a high level language like C, and those high level code are going to be there. That code, high level code, is going to be converted into something like this at the end of the day, because at the end of the day it is the assembly instructions that the computer can understand. So the first arithmetic operation that we can look at is the addition operation. So subtract operation is also going to be very similar, and add, subtract, both these instructions, they have 3 operands. So if you look at this instruction, add ABC, so this is an this is the addition operation supported by the ARM processor. And you can look at what this means. Now there are 3 operands here, or 3 parameters given to the add instruction. Now this is the instruction name, and these are the 3 operands that we are giving to the add instruction. So this A, we call it the destination operand, and B and C, we call them the source operands. So addition, you all know what addition is. A equals B plus C, something like that is, we are calling something like that an addition. So when you want to perform that addition using assembly, you need to use a command like this, add A, B, C. So the result of this instruction will be that B plus C value will be put to A. So in C, you will write something like A equals B plus C. And if you consider all the other arithmetic operations, so they all have this same form. So if you want to perform a subtract operation, it will be something like sub ABC, which will perform A equals B minus C operation. So these are the basic operations that the CPU or a processor can do, and all the complex operations you are defining in a high level language, they will be converted, they are going to be converted into things like this. And this is the form of the arithmetic operations. And with this, we can talk about a basic principle used in hardware designing, that is simplicity favors regularity. And can see what it says here. Hardware for a variable number of operands is more complicated than for a fixed number. Now here in the add operation or the add instruction, we saw that there are 3 operands. And if you consider all the other arithmetic operations, they are going to have the same form. They all have only 3 operands. So this uniformity or the fixed number of operands you can see in most of the assembly instructions. So this is there to reduce the complexity of hardware. So if you have simple hardware, then that means that you can perform that operation with a higher performance. Now, say if you are going to support instructions that can take variable number of operands. So then if you are going to design a hardware processor that can perform these operations, then that hardware will have to check the number of operands available in the instruction, and then it needs to do the calculation. And if you support variable number of operands, then the hardware is going to be, of course, complex. So if you have a fixed number of operands supported by the instructions, then the hardware is going to be simple, and that can lead to higher performance. So this is the design principle 1. Simplicity favors regularity. So if your operations are regular, then like regular meaning the number of operands supported by instructions are the same, and they are simple. And so if you have this regularity, then the implementation is going to be simple, and this simplicity enables higher performance at lower cost. Of course, the cost is also going to be minimized because the hardware design is going to be simple. So this is the design principle 1 of hardware designing, and we already have looked at a practical application of this design principle with the uniform arithmetic operations. Now here you can see an example of an arithmetic operation. So here you can see a C code written to calculate something. That something is g plus h minus I plus j. And in C, you can easily write this line of code to get this calculation done. F equals g plus h minus I plus j. But when you are going to do this with a processor, and if you are going to write this program in a language that the computer can directly understand, then you will have to write this program instead of this one, because a C compiler, before it executes that program, it compiles this code into something that the computer can understand. That something the computer can understand is assembly. And now here in this course, you are writing programs. You are going to write programs directly in assembly. So that is like you are performing the compilation step yourself. So if you look at the compiled ARM code of this C code line, then it will be going to look something like this. Now here we are first performing an addition operation at T naught GH. So we already looked at how add operation works in ARM. So after you do this, after you execute this instruction, this T naught will get the addition of G plus H. And now with the second line, what we are doing is we are making T1 equals I plus J. So at T1 Ij, what it means is T1 equals I plus J. Now you have these two additions with you, and now you can perform this subtract operation. Now for this subtract operation, you can use a similar instruction, an instruction similar to that instruction. So this instruction, we call it sub, and you can perform the sub operation by using this instruction sub f t naught t1. So this will do this final subtraction, and finally for this f variable, or more precisely f register. So you have not looked at registers and all that yet. A little later we'll look at that as well. So all these operands, we call them register operands, and at the end, for f register, you will get the subtraction of t0 and t1. Is it clear? So next slide will talk about these operands a bit in detail, a bit more in detail. So if you have any issues so far, you can raise them. Is it clear to you all? So what we covered now, it's anyway is very simple. The only thing is that you might not be very familiar with assembly programming. Is it okay for everyone? Since this is the first tutorial session, we will be going slowly, and if you have any issues, you can ask them here itself without waiting until the last moment. So this is how you can basically compile a C code into ARM assembly manually. Earlier in your programming course, the compiler did this task for you, but here we are writing programs directly in assembly. So you have to do the compilation yourself. And the compiled ARM code for this C code line will look something like this. And I hope it was clear to you all. So assembly instructions, they support only 3 operands. You cannot perform this code line, or you cannot calculate this. You cannot do this calculation with a single instruction, because assembly instructions, they only support 3 operands. So you have to break this operation into parts and do the calculation. So was it clear to you all? I would like to get a response. Otherwise, I'm just talking. Because here in tutorial and lab sessions, okay, good. Because here in tutorial and lab sessions, you will be looking at practical application of assembly and computer architecture. Good. Okay, thank you. So we'll move forward. Now we can look at the operands in real hardware. So earlier in C, you will call things like these variables. Things like f, g, h, you were calling them variables, and you were not thinking about where these variables are and how they are going to be stored and all that. You might have not thought about all that in detail. But here, since we are going to hardware level, hope the audio is now clear. Now we look at what these operands mean in real hardware. Now, all these variables you have looked at it in C, they are going to be stored, or they are going to be stored in the processor to perform all the calculations and the operations you are defining in C. So these operands in instructions are registers in hardware. So registers, you already have looked at what registers are in your digital design course, I hope. So registers are things that can store data. So if you take a 1-bit register, or maybe 8-bit register, an 8-bit register is made up of 8D flip-flops that I think you all know by now. So a register is made up of 8D flip-flops, and these registers are the ones that are going to store these operands. So you first need to store the operands, and then only you can perform all these operations. Addition, subtraction, all that you can do only if you have stored those operands. The operands required by the operation, you need to store them somewhere in hardware. So we are storing these operands in registers in real hardware. So things like T0, GH, T1, IJ, all that, we call them register operands because these values are going to be stored in registers in real hardware. So we call all these register operands due to this reason. And unlike in an high-level language, the number of operands in instructions are limited. So this is due to the obvious reason that the hardware is limited. You cannot have a hardware circuit that can adapt based on the program that it executes. So once you have the circuit, the number of registers are defined already. So the number of elements or number of storage elements that can store these operands are defined by the time you are done with the hardware implementation or the processor implementation. So the number of operands supported by assembly instructions are limited. That is because the hardware is already defined. And in a high-level language like C, you had the chance to define variables as much as you want. But here, the number of variables that you can have at the same time are limited. So you will understand this better when we go into real assembly programming. Okay, so this concept you need to have in mind. So if you consider ARM processor, the number of registers available in the ARM processor is 16. So in ARM processor, you have 16 registers, each of which are 32 bits in size. So it has 16 32-bit registers. So the set of registers, we call it the register file as well. Now you have seen 8-bit, 4-bit registers in real hardware in your previous digital design course. Here in ARM processor, you have 16 32-bit registers. So you can use only these registers to store operands. Operands meaning for an addition operation, for an instruction like add A, B, C, you need to store B and C operands first in a register, and then the result is also going to be stored in another register called A. So for 3 of these operands, you need to allocate 3 registers out of these 16 registers available in ARM processor. And these registers are used for frequently accessed data, and these registers are numbered from 0 to 15. So you have 16 registers in ARM processor, and we call them R0, R1, R2, R3 up to R50. So each of these registers are going to be 32 bits in size. And also there's a term commonly used in this course and computer architecture generally, in computer architecture and assembly. This is word. So this word refers to 32-bit data. So if you consider a register, hardware register, it can store a single word. That is because a word is a 32-bit data. 32-bit, like that is like 32 ones and zeros. So if you group 32 ones and zeros, we can call it a word. We call it a word, and a word can be stored in a register in ARM processor. And something is happening with the presentation. Okay, so you have 16 32-bit registers, and you might see that in C, when you are defining variables for a typical program, you might get the need of defining variables. So we have been looking at the number of registers available in the ARM processor, and now when you're programming something with C, you get the need of having a lot of variables. Something like, for example, at the same time, you might need to have 30 variables, for example. Now here in hardware, you have the support only for, it has the support only for 16 operands. That means that you can store only 16 variables at the same time. So you initially you might feel like it's better to have as many as possible registers in hardware level itself, something like 30. But if you have such number of registers, very large number of registers, it can increase the clock cycle time. So this is because the hardware circuit is going to be large when you have a lot of hardware components. Here, a lot of registers. So when you have something like 30 registers, then it's going to make the circuit larger, and the electronic signals has to travel farther. So because of these reasons, the clock cycle time has to be increased. So which makes your design slower. So if you want to have a faster implementation, or like a processor that is faster, you need to make your circuit as small as possible. But for programmers, it is necessary to have as many as registers. Now there's a trade-off between the number of registers required and can be supported by the processor. So designers should balance the craving of programs for more registers with the desire for fast clock cycles. Now ARM has decided to have only 16 registers. So looking at both these ends. So smaller is faster. So this is the design principle too. Now, register operand example, we can formally look at register operands here. Earlier, we were having the same C code line earlier as well, f equals g plus h minus I plus j. And so all these values, g, h, I, j, and the result also, they have to be put into registers available in ARM processor. Because at the end of the day, they have to be stored in real hardware. So in this example, we are going to store f in R0, g in R1, h in R2, I in R3, and j in R4. And you will see, to perform this calculation, in addition to these R0 to R4 registers, you need some intermediate temporary registers as well, because with one step you can perform only one operation. So R5 and R6, we take them as temporary registers. So because we have 16 registers, after using 4 of these registers, you still are left with 16 minus 4 registers, that is 12 registers. So you can use these R5 and R6 as temporary registers. Now we are going to do the same basic operations as before here, but using correct register symbols or correct register names. So R5, for R5 we are going to get the addition of R1 and R2. For that you can use this add instruction, and then this I plus j operation you can perform with this second add instruction, add R6, R3, R4. And now R5 and R6 contains these two additions separately, and now you finally need to do this subtraction operation to get the final value f, and final value f is going to be stored in R node. So that is what we have decided earlier, to store f in R node, and so we can put the result of R5 minus R6 into R node register. So always for these arithmetic instructions, the destination is going to be the first operand. So the first operand is going to be the destination. That is, the result is going to be stored there, and the other two are going to be source operands. Here in this example, R1 and R2 are source operands. So this is about it. And if you have any issues, you can always interrupt me at any time and then ask. Now that we have looked at how you can use ARM assembly to write a assembly program, we can now go into practical assembly programming. And for practical assembly programming, you need two tools. I think you already have been introduced to this in brief in your introduction lecture as well, and we already have posted a notice to instruct you how to install these tools on your computer so that you can write and compile and run assembly programs on your computer. And the first tool that you will need when you are going to compile and run assembly or ARM assembly programs is this cross compiler. Now the GCC, you already are familiar with GCC because in programming methodology course you use GCC. And so that GCC, when you are executing this GCC tool in your computer, GCC tool is going to generate an assembly program or a binary that can be executed on your on the processor that is available in your computer. So that is, if you have a PC with an Intel processor, it is going to generate an assembly that can be executed on an Intel processor. But here we are looking at ARM assembly, so we need to get a binary that can run on an ARM processor. So the typical or the usual GCC you have in your computer, you cannot use it to compile ARM assembly programs. Here anyway, with compilation, you will be most probably doing only the assembly operation, that assembling. We call it assembling because you are writing the program in assembly, and the only thing you need to do is the main thing you need to do is to convert this assembly into machine code, that is ones and zeros. So for this assembling operation, you cannot use the GCC because it is going to generate a machine code that can run on your processor, the processor available in your computer. So for this purpose, we have to use a cross compiler. The cross compiler we are going to use is called this GCC ARM Linux GNU EABI, and you can install this tool GCC ARM Linux GNU ABI by using this command. I hope some of you have already installed, most of you have already got it installed on your computer. If not, you can perform this operation or perform this command on your Linux machine to get it installed. And this is the first tool that you will need to compile ARM assembly, and then emulator. There's another tool that you will need, which is called an emulator. Now, even if you have the by using a cross compiler, you can generate generate a machine code that can run on an ARM processor, but still you don't have a ARM processor with you. Now this ARM assembly or ARM machine code you can run only on an ARM processor. Since you only have an Intel processor, you need to have a tool that can emulate the behavior of an ARM processor. So this program, we call it an emulator, and we are using this emulator called Kisaru to run ARM assembly or ARM machine code, ARM binary on your Intel machine. This also you can install by using this command on your Linux PC, Kisaru user. This is the tool that you will need. And you first need to cross compile, and then using the emulator you can run the assembly binary that have been generated by the cross compiler. And if you look at the basic things about an assembly program, the assembly program code, you save it with this .s extension. For C programs you use .c extension. Here the extension you will be using is .s, and comments in assembly start with @ and also you can use these double slashes as well. Double slashes used in C as well. Here @ also you can use for single line comments. And things starting with dot are called assembler directives. So you, in a typical assembly program, you will see things like .text, .global, things like this you will see. So these parts, we call them assembler directives. We use them to direct the assembler. Compiler directives, I think you have seen compiler directives in C. So these are going to be similar to that. And the assembler is the program that converts instructions to machine code. Now, even the low level program you can write is the assembly program. Now, even the assembly program, the processor cannot directly run an assembly program. That is because assembly program is written in a high, a human readable format, that is add R0, R1, all that are just human readable symbols. So text we are using. If you want to run a program on a computer, you need to convert all that into ones and zeros. That is like a direct mapping between for add operation, for add string, you can have a particular one and zero string. So all these things you will look at them later as well. So the program that we use to convert the assembly program into machine code, that is ones and zeros, that we call it the assembler. Now here with this cross compiler, in the cross compiler, the part that we'll be using is the assembler part, and one instruction per one line. So when you're writing assembly programs, you can write only one instruction per line. Assembling and running, you can assemble a program using this tool you have installed on the Linux computer by using this command, ARM Linux GNU ABI GCC. This is the tool that we use to cross compile this into an ARM processor, and then the rest is very similar to how you compile a C program. So when you are compiling a C program with GCC, you use this wall to activate all the warnings, and then this is the source file. Example.s is the file that contains our assembly program, and then dash show example. This tells the name of the binary that it should generate. So example.s will be converted into machine code, and it will be put into example file. And now you have the compiled ARM machine code, and now you need to run it on an ARM processor, but you don't have an ARM processor with you, so you have to use an emulator. In this course we are using this QEMU-ARM emulator, and to run the QEMU-ARM emulator, you can use this command QEMU-ARM-shell. You use ARM Linux GNAVI. So this you have to link, and then here you have to specify the binary that you generated with the cross compiler. It is the same name you gave here. So that's about it. And here we have an exercise for you to try, and I can show you how you can perform this or execute these two commands to assemble and run a program, but that is going to be very simple, just running these two commands on a Linux computer. We have a hello world program written in assembly. I will show you, maybe I'll show you how you can compile and run the hello world program. But one thing you need to remember is that the hello world in assembly is not as simple as hello world programs you see for other languages, because to print something to a command line with assembly, you need more stuff. That is, printing something to a command line, when you're going to do it at assembly level, you need to perform like some operation that you are not familiar with yet. So the hello world program for assembly, ARM assembly, might not be very clear to you yet, but that's okay. You just don't need to think too much about the content of the hello world.txt file we have given to you. So these programs we have given to you under the tutorial 1 files. Can you see me? Can you see my work? Okay. Yeah. I have the hello world.txt assembly file, and the content of this file, you don't need to worry about that, because there's a lot of stuff that is going on here which might not be clear to you yet. The only thing you need to do here is to practice how you can compile and run this program. Now you can use this command ARM Linux GNAVI GCC -wall hello world.txt -o hello world. So this will compile, cross compile this into an ARM architecture, and then you can run the program that you already have compiled by using this QEMU-ARM command. So it will print the hello world command to the command prompt. From command prompt. So you can test it, and then there's an exercise for you to try. Exercise 1, the second part of the exercise 1, of course. You have to complete ex1.s to do the following calculation. It has this calculation: f equals a plus b minus c minus d plus e. So this you have to do with assembly, and we have already given you a skeleton code. That is because you still don't know how to print something to the output, and how to put values to registers and all that. You have not looked at them yet. You only know how to perform arithmetic operations so far. So because of that, we have given you a skeleton code, and you need to write your code here only. Here in the page we have defined for you to write your code. So you can use this page to write your code, and now you can assume that actually we have put these A, B, C, D, E values into R0, R1, R2, R3, R4 registers respectively. So you need to put the result F to R5. Can you all try that? You can try that, and if you get into any issues, you can let us know. I hope these files are with you. They are already uploaded on fields, so you can download if you have not done it yet. And you can try this out, and then the rest of the code that is in the skeleton code, you don't need to worry about that yet, because you have not studied about those things yet. You will of course learn them later in the course. Has anybody tried to do it and compile it? You first need to have these tools installed on your computer. And for Windows now, there's something called Windows Subsystem for Linux. So if you have not, anyway, I hope you all have installed Linux on your computers, because you have been doing the labs on Linux. You can use just Linux or WSL to compile and run your code. If something was not clear, just let me know so that I can explain it again. Otherwise, if you don't have an idea about what we are doing here, then it's going to be hard for you to understand the rest, because the coming parts are going to be more advanced. If anybody tried doing this, let us know. Like,
guys, everyone should try the exercises as Kisaru is explaining them, because otherwise if you try to do this later and run into issues, it will be difficult for you to complete the labs on time. So try it now itself and let us know how it is going. It's perfectly working fine, or if you have any issues.
so if you could compile and run and could get the expected result, then you can let us know. Okay, great. Okay, Akila has got the correct answer, and so likewise others, you all should try actually now. Okay. So when you want to perform an arithmetic operation on the data available in main memory, you need to first load those values into registers. And now you have loaded the values into registers, and now you can perform the calculation needed, arithmetic operations, up, add, sub, anything like that. And then finally, once you are done with the operation, the result you have it in a register. Now the result also, you might see that the result also, it is not like the register space is not enough to store all these results. So if that is the case, then you need to store this result also back in the main memory. So these are the two things that two operations that you will be performing with the main memory. So when you want to perform an arithmetic operation, you need to first load the values from memory into registers, and once you are done with the operation, you need to store the result back in the memory. So that is it. Now we will look at how you can load and store values from main memory and to main memory with instructions that we will look into it a little later. And before that, you will need to know how the memory is addressed or accessed. For that, maybe I'll have to use a diagram. Now, there's something called byte address memory. So memory is byte address. That is, if you take a memory address, let me open up something. So hope you can see my sketch. I'm sharing the sketch. So if you consider the memory, it's going to be something like this, where you can store values, multiple values. And if you consider these blocks, if you look at these blocks, you can see if you this is here I am drawing a sketch of the memory, main memory. So you are going to store values in this main memory. Each of these blocks, in each of these blocks, you are going to store values. And if you consider this first block, this block can have the memory address 0x00. So memory addresses, we usually address them using hexadecimal notation. And this address could be addressed as, it is addressed as 00, and now the next address is 01, and the next one is 02. So you can go like this. So each location in main memory is given a different address, and if you look at the size of these size of each of these blocks, it's going to be a single byte. So that is what is meant by this. Each address identifies an 8-bit byte. That is because when you consider a single memory address, it can store in that location, it can store a single byte, that is 8 bits. So 1 byte you can store here, and then the next byte you can store here in 01 address, and the next byte you can store here 02. So each byte in memory is given a unique address. So that is the concept of byte addressable memory. So you can give 02 to this byte, and then 001 to this byte, and this byte you can give 02 address, and likewise you can go on addressing the memory. So in one address you can store only 8 bits. This idea you need to have when you are accessing the memory. So all the addresses you are giving, like when you are going to access the memory, you need to use the memory address. Like when you are going to load something from memory, you need to use the memory address to load something, and when you are going to store something, there also you need to use the address. And here you need to keep in mind that each byte in memory is addressed. Now And also the other thing is words are aligned in memory, which is called, so this is called, this is also called as alignment restriction. Address must be a multiple of 4. So when you are going to store a word, when you are going to store something in memory, the address to which you are storing, it should be a multiple of 4. So this idea, if it is not very clear to you now, you can forget about it for now. But this memory, byte addressable memory, that should be clear to you all. And also with ARM, there's something called ARM is a little endian. So there are two concepts named as little endian and big endian. So this also we look at in this next slide a bit in detail. So ARM, we call it little endian. In little endian notation, the least significant byte is stored at the least address, and in the big endian notation, most significant byte is stored at least address of a word. So this idea, it will be more clear with this diagram. Now I told you that memory is something like this. Now this block is memory. Here also it is memory, and we need to store a word in the memory. Now I told you that when you run out of space in the register file, that is, you don't have enough registers to store all the variables that you need in your program, then you need to go access the main memory and store that value in the memory. Now when you are going to store a word in the memory, so because in processor you are dealing with words, that is 32-bit integers or 32-bit binary values. Now an integer also, you can store it as a integer is stored as a 32-bit value binary pattern. Now you have this 32-bit integer value, 0A, 0B, 0C, 0D. This is the word that you need to store in the memory. And when you are going to store it in the memory, there are two types with which you can store this integer. Now the two types are called little endian and big endian. We can look at this little endian notation. In little endian, what happens is, now this 32-bit integer, you can break it into bytes. The first byte is 0A, second one is 0B, 0C, 0D. Likewise, you can break this into bytes because 1 hexa. So this is written in hexadecimal notation. 1 hexadecimal digit is 4 bits. So 1 byte, you need to take 2 hexadecimal digits to get a single byte, 8 bits. Now, when you are going to store this in memory, within little endian notation, you are storing the least significant byte. That is here in this example, that is 0D. 0D is stored in the least memory address. Now these are the memory address: A plus 1, A plus 2, A plus 3. So we are using a general notation here. A could be 0. If A is 0, then this is 0, 1, 2, 3, likewise. So each byte is given a different address. A plus 2, A plus 3. Now with little endian, you are storing the 0D byte in A address. That is because the least significant byte is stored at the least address, and 0C is the first byte. If you call this the 0th byte, this is first byte. 0C is stored at A plus 1 location, and 0B is stored at A plus 2 location. 0A is stored at A plus 3 location. So this is how you store words in memory with little endian notation. If you consider big endian, you are storing the most significant byte. This is like the other way around of little endian. 0A is the most significant byte. You store that in the least address. 0 is stored at A address, and then 0B is the second most significant byte. So that is stored at A plus 1 location, and 0C is the next one, that is stored at A plus 2. 0D is that is like the least significant byte in this 32-bit integer word, 32-bit word. So least significant byte is stored at the highest memory address, that is A plus 3. So this idea you need to have. This is like a like anyway, the ARM processor we are talking about, it uses this little endian notation. So if when it tries to, like when it stores a value in memory, it stores the least significant byte of the word in the lowest address. Okay, so that's it. If it was not clear, let us know. Hope it was clear. So that is basically how you store a word in memory. And there are two types or concepts that are used to store words in memory. And ARM uses the first type, little endian type. And when you are going to practically use the memory to store things and load things from main memory, you are using just instructions to do them. So you actually, when you are programming with assembly, you don't really worry about whether it's little endian, big endian, and all that. But since you are learning how things are happening under the hood, so you need to know all these things. But when you are programming something, or when you are writing an assembly program to access memory, then you will be doing that just with instructions. And the instructions that you will be using to access memory, there are two types, LDR and STR. So mainly there are two instructions to access the memory. That is LDR instruction and STR instruction. LDR instruction, this instruction we use it to load the word into a register. So I told you that when you want to perform an operation on elements or values stored in memory, you first need to load that into a register. To do that, you can use this LDR operation or LDR instruction. And when you want to store the result back in the memory, you can use this STR instruction. So this is a memory operand example. Now here you can see there's this C code which deals with memory. G equals H plus A8. Now here you can see that A8, this one is a array element. It's an array element. So you need to perform an operation on an array element. Now we are assuming that this array is not stored in registers and it is stored in memory, because an array is well suited to be stored in the memory, because it's going to have a lot of values, elements. So the register file is not enough to store all that. So that is stored in memory. Now, when you want to perform this calculation, G equals H plus A8, you need to first load this 8th element of A array into a register, and then H is stored in, we can assume H is stored in a register. That is because it's a constant, or it's not an array element actually. So it's stored in a usual, like a normal register in the ARM processor, and you need to perform the operation with this array element. Now we are assuming that G is in R1, that is the result is to be stored in R1, and H is in R2, that is a normal register, and the base address of A is in R3. So when you are dealing with memory and arrays, you come across this word base address. Now the base address is the starting address of the array. That is like you can have 10 elements in the array. The location at which the 0th element is stored is, we call it the base address, because that is the start of the array. And now the base address of A, we are assuming that it is stored in R3, and we need this R5 temporary register as well to perform this computation. So R5 is a temporary register, and now we can you look at the compiled ARM code. Here the indexing is the thing that you need to really worry about, because other things we already have looked at them. Here index 8 requires offset of 32. Now we told that the memory is byte addressed, and also these elements we are assuming that they are 32-bit values. So A0 is a 32-bit value, A1 is a 32-bit value. Again, likewise, A8 is also a 32-bit value. So you can assume it to be an integer, and this integer is stored in memory. So it needs 4 bytes in memory to store its value. So index 8 requires offset 32 means that you starting from the base address, you need to go 32 bits, like further, or like we need to do we need to have a sketch to explain this? Try to understand it like this. If it is not clear, let me know. So LDR, now LDR instruction, instruction, we are going to use it to load a value from main memory to a register. So that we all know. And the first operand for this LDR instruction, this R5, is the destination register. That is, you are going to read a value from main memory and you are going to load it to a register. The register to which the value is loaded is R5 here, and this part R3 comma hash 32. This is the interesting part. Now base address, we know that it is stored in R3, and the 8th element is stored 32 bits far away from the base address. That is, for a single element, it takes 4 bytes. And if you want to access the 8th element, you need to go for 8 into 4, 32 bytes away from the base address to access that element, because each byte is given a separate address in memory. So if you say R3, that is the base address, and if you say R3 plus 1 address, that address still points to somewhere in memory that has the 0th element of the array. And if you want to access if you really want to access the second element of the array, you need to go to R3 plus 4 address. I hope this idea is clear. And if you want to access the third element, then you need to go to R3 plus 8 element, 8th address. And if you want to access the fourth element, you need to access R3 plus 12 address. And likewise, this address offset is given here. That plus something value, that value you need to specify here when you want to access the 8th element, or when you are using the, like, if you start indexing from 0, it's going to be 8th element. Basically, that is going to be the 9th element. Because we are using 0 indexing here. So to access the 8th element, you need to add 32 to this R3, and then only you should perform the load operation. So that memory offset is specified here as an immediate value. These things we call them immediate values. Hash 32, you have to use it. And then the addition is this we already have looked at how you can do addition operation. It's a basic addition. You have the A8 value in R5 now, and you need to add R2 or H value of H2 R5 and get the result stored in R1. So for that you can use the second add instruction. Is it clear how you can load the value from main memory to a register in the register file? If it is not clear, let me know. I can maybe explain it again with a sketch or something like that. Is it clear how you can access memory? Next, there's an example that deals with the store instruction as well, and also some more ideas. So you first need to be very clear with this one, how you can load a value from main memory to a register, and how you can use this offset and base register values to store a value or load a value in an store like a array element, if when you want to access an array element stored in memory. So is it clear? I would like to get a response from you, because we can use Friday slot as well for this tutorial session, because this is the first one. Okay, great. Okay, seems like you have understood it. So if you still have any issues or concerns or need more clarification, you can let us know later as well. Now here with this memory operand example 2, we are going to look at the store instruction as well. Now here we have this C code that operates on an array element, and also it is stored back in the main memory. The result, earlier we were not storing the result back in main memory because the result was just a register. Like the result was stored in just a register, but here it's also going to be stored in another array element. So array we have here is the same array A, and H is in R2, base address A of A is in R3, and R5 again is a temporary register. Now if you look at the compiled ARM code for this C code, when you want to access the 8th element, the offset is still the same, because you want to access the 8th element, and actually these first two instructions are the same. They are same as the previous example, because you are loading the A8 value to R5, and then you are performing the addition with R2 and R5, and then finally this result, which is in R5, now you need to store it back in the memory as an array element. For that, you can use this store str operation, store or str operation, str instruction, and the value to be stored in main memory is now in R5 register. So that is where we put our result into earlier, and this result R5, we need to store it back in memory in this location, A12th location, A12. Now the offset value for this 12th element is, if you compute it, that is going to be 12 into 4 bytes away from R3 base address. So you need to use the offset as 48, and that's it. Base address still is in R3 plus 48 address. You will be storing this value in R5 in R3 plus 48 address in main memory. So that's it. So it's very similar to LDR. The only difference here is that you are storing something in the memory. Like you take the value from the register file and then you go and store it in the main memory. Hope that's also clear. If it was clear, like if LDR was clear to you, then STR is not very difficult. Yeah. And now we can see the difference between registers and memory. Registers, if you consider the registers, they are faster to access because registers are there in the processor itself. You don't need to go anywhere else to access registers. Registers reside in the processor itself, so they are faster to access. And when you want to access the memory, it takes more time. because you are accessing another device. And operating on memory data requires loads and stores. So when you are operating on memory or data available in memory, then you need to perform these additional operations, load, store operations. You need to execute them to load something from the memory and then store the result back in the memory. So that means you need to execute more instructions. So when you have more instructions to be executed, then that's going to take more time to run your whole program. So compiler must use registers for variables as much as possible. So because of this reason, so the memory accesses are actually going to be expensive. So they are costly. So when you have memory accesses, it's going to consume more time. So compiler should try to use as much as possible like it should use registers for variables as much as possible. So it should spill to main memory for less frequently used variables. And of course, if you need to store a lot of values, a lot of elements, something like an array, then of course you will need to use main memory. Only if you need it, you should do it. That is the idea here. Register optimization is important. When you are using registers, you need to optimize the usage of registers so that memory accesses are reduced. You need to reduce memory accesses as much as possible. So that is the idea. Now there's another example or exercise actually for you to try. It's the skeleton code is given in ex2.s and you need to complete that skeleton code to get this done. Base address, now here you of course will need to perform memory operations. Now these values, like we have already loaded the memory with these values, so you don't need to think about loading initial values to a array and all that. You don't need to think about them because we already have loaded the initial values to a array in the skeleton code. All you need to do is to load necessary values to registers and perform the calculations, and then finally you will need to store the result in the array. So now the base address of this A array is in R node, that also you can assume, and the value B, which is a constant, that is in R1. And you can use, of course, you will need to use temporary registers even for loading and calculations, all that. You can use temporary intermediate registers. And finally, A2 value, the memory, second element of A array should be loaded with the result of this operation or the calculation. That you can try now. We only have around 10 minutes left, I think. There's a little more theory about immediate operands that we will discuss Friday. Now you can start working on this one, and we will finish the lab at 11. If you have any issues regarding memory accesses, let me know so that I can explain it again with a figure or anything like that. If you need further explanation, just let me know. Don't wait until you get to the lab, because there's a lab exercise which will be marked. So these exercises, they are for you to try, and they are done in the tutorial. And there's a separate lab exercise which will make use of all these theory you will learn in the tutorial class, and you will need to apply them to complete that lab, and that will be marked. So if you have issues about these concepts, then you can ask about them here itself without waiting until the lab comes to you. These slides are already available in fields. They have been uploaded to fields already. So if you want to refer to them later, you can of course use them. Anyway, I got responses only from 3. I'm assuming that the others also like this is clear to others as well. Great. Okay, one person has already got the answer as well. If you were unable to get the answer, that's okay. Just let us know. Don't think like others are doing it. So I should not ask for a clarification. Don't think like that. If you have any issues, just ask. Okay, we have got a question about LDR and STR. Yeah, in LDR, what we are assigning is in the right side, and in STR, it is in the left side. Yeah, that is how these instructions are defined, and that is how they are encoded and all that. So how instruction encoding happens, you will learn about it later. Anyway, these instructions, they are designed like that. So the one that the value loaded from memory is stored in the register which is specified as the first argument in LDR, but in STR, that is like the value of R5 is stored in R348, because to make the memory address part placed as the second argument of the instruction. So that is again like make things uniform and all that. So that's a good question. So things related to memory. So memory addresses, we are always stating them as the second argument of the instruction. So that is why we are having this standard. So in STR, we are taking this value and storing it in the R5. So this is in STR, we are taking the value in R5 and storing it in R3 plus 48 address. Here R3 plus 32 value in memory, we load it to R5. So this is like source and destination. Maybe you can think it is switched, because you read this and make R5 equal to this, and you read this and you make this equal to this. So that is how it is standardized. That's a good question. Anyway, like it's good that you noticed it, and so if you have that idea in your mind, then you will not use it properly. You will, like when you are using LDR and STR, you will place the arguments in proper places if you have that idea in your mind, that I should put the destination here when using LDR, and you should put the destination here when using STR. So that idea you need to have. Any more questions? We will have to end this session sharp at 11. If you still have any issues, let us know. You can use the WhatsApp chat and also the discussion forum available on Field. So you have a lot of resources to get help. Use one of them to get help, and we are left with like a very tiny part here in tutorial 1. So that we will look at it in the next session, which will be scheduled on Friday. Friday we'll have the next session. That is going to be 1 hour session. Immediate operands. That's a very like a simple part anyway, but I didn't want to rush into that without letting you try that out. Try the memory part out. You can of course look at it in the slide and try to understand and apply it. So you can try to complete the part 2 of exercise 2 as well. And in next week you will do the lab 1, which will be marked. So we will get the help from casual instructors as well. Okay, I hope we can end the session now.